Welcome. Let's take a look at that RC circuit. So we're going to draw an RC circuit with a switch, a resistor, a capacitor. Our resistor is going to have a value of R, our capacitor is going to have a value of C, and our capacitor is going to start with a maximum charge on the plates. So what is going to happen is that the charge at time equals 0 is going to be Q max. And then after we flip this switch, right, all of the charge is going to go through here and eventually discharge the capacitor. We don't know how long that's going to take, but we know after an infinite amount of time, the charge will be 0. So with this, we can do Kirchhoff's loop rule just like we did in the previous video. And so we get negative Q of as a function of time minus R times I as a function of time equals 0, because we only have two elements. And we can use that I as a function of time is defined as dq of t dt. So then we get negative q of t over c minus r dq of t dt is equal to 0. And we're going to solve for dq of t dt. So what this gets us is dq dt equals negative 1 over rc times q of t. And as we said, this is a differential equation. The rate of dq dt depends upon the initial value q of t. So one thing we can do is what's called separation of variables. We want to bring all the q's over to one side. We want to bring anything that's not a q to the other side. So what we are going to do is we're going to treat dq and dt as separate values, because in physics, dq represents a small amount of charge and dt represents a small amount of time. So we are going to multiply by dt. We are going to divide by q. And so this gets us 1 over q times dq equals negative 1 over rc dt. And so now we see that we have the setup for an integral. So we want to take an integral. So we have 1 over q of t dq dt. So we're integrating over charge on this side, and then we're integrating negative 1 over rc dt. We can pull that negative 1 over rc out. But we are integrating over time. We're integrating from time equals 0 to time equals t. And so we have, right, q equals q naught to q equals q as a function of time. Well, this side is really easy, right? We only have t, so we have this is negative 1 rc times t minus 0, or we can just say t. Here, we have that this is q of t, so that gives us a natural log. So now we have natural log of q of t, and we're going to evaluate this from q naught to q of t. So I can write this as either q of t minus q naught, or I can write it as a ratio q of t over q naught. And then this is still negative t over rc. So if I want to get this q of t out of this natural log, I need to take the exponential of both sides. Taking the exponential of both sides will give me, right, e to the natural log of q of t over q naught is just equal to q of t over q naught, which is then equal to e to the negative t over rc. So one last little step to go. We've got charge as a function of time, multiplying both sides by Q naught equals Q naught e to the negative t over RC. Excellent. So let's check this. Our charge at time equals 0 is equal to Q max. Well, I can put in 0 for here, so that would be Q naught times e to the negative 0 over RC. E of 0, whether it's positive or negative, is just 1. And so I get that Q max is Q naught. So every time I see Q naught, I can replace it with the initial maximum charge that this had. And then I can also check and see what charge at time equals infinity will be. Well, I know it's going to be 0. And then I can plug infinity into here, so I have Q max e to the negative infinity over RC. E to the negative infinity will get me that all of this goes to 0, which means all of this goes to 0. And I get very nicely that 0 is equal to 0. Not necessary, but certainly heartening to know. And certainly heartening to know that all of this works. So this is one way that we are going to solve these differential equations, is by doing a separation of variables and then taking integrals.